Okay, and the next topic is unsteady state one-dimensional heat conduction. Okay, one-dimensional unsteady state heat conduction. Okay, now when we talk about unsteady state heat conduction, okay, what are all the examples, right? What are all the examples which, um, especially in mechanical engineering, what are all the examples which we have, especially for unsteady state heat transfer? Okay, especially the cooling of ice engines, cooling in injection molding of thermoplastics, heat treatment of metals, casting, and processing equipment, bringing processing equipment to steady state. Okay, so these are all some of the examples for unsteady state heat transfer. And of course, we will be discussing in detail about what is Biot number, which is a dimensionless number, which is nothing but ratio of conductive resistance to external conductive resistance or convective resistance. Okay, so we will discuss about that. Okay, so the very practical example of especially in case of mechanical process, the very practical example for unsteady state heat transfer is uh, that is dropping a solid which is at a very high temperature. Okay, dropping a solid which is at a very high temperature into a fluid. Okay, which is at a very lesser temperature. Okay, so that heat treatment process. Okay, so that the strength of the material increases, or otherwise in case of food industry, as I mentioned earlier, right, dropping a food which is at a lesser temperature into a zone where it is at a higher temperature. Or similarly in case of furnaces. Okay, in case of furnaces, what happens is we will be there is inserting the metal rods into furnace. Okay, so that what happens is the rods get heated up. Okay, so especially in case of casting industry, okay, we will be using it. Okay, now when we talk about lumped system, okay, so there are several methods by which um, we can go for what's that we can find out solution. Okay, we can find out solution. One particular system is said to be lumped system. Why it is said to be lumped system? Because as I mentioned earlier, right, dropping a solid, okay, which is at a very high temperature into a fluid which is at a very lesser temperature. Okay, so now what happens is, especially there is a one heating process known as Newtonian heating, and there is one cooling process known as Newtonian cooling. Okay, so what is meant by Newtonian heating and Newtonian cooling? So you may ask a question. See, whenever a hot solid is dropped into a fluid at a very less temperature, as I mentioned earlier, the heat treatment process, the hot rod, right? The hot rod, which may be at a or a hot coil spring. Okay, for example. A coil spring is a very good example. The hot coil spring, when we drop it, when we quench it in water, what happens is after a few minutes, okay, the temperature of the coil spring reduces. Am I correct or not? Am I correct?
Yes, sir. Yes, sir.
Okay. Now what happens is, so in that case, the internal resistance, we know that the internal conductive resistance, we know conductive resistance is given by L by Ka. Am I correct? Especially in case of solids. L by K is the
Yes,
conductive
sir.
resistance. And what about the convective resistance? Convective resistance is, we know that. Okay, let me write it here. Okay, instead of let me write it. Hello, is it visible to you all?
Yes, sir.
Is it visible, ma?
Yes, sir.
Okay. Now
Yes,
we
yes.
know that. Yeah, let me write it out. We know that Q conduction is minus Ka dt by dx. Am I correct, ma?
Yes, sir.
Okay, or we will be writing this as uh, minus dt divided by dx divided by ka. And usually in case of uh, small slab of thickness L, okay, and area is nothing but the area which is normal to the flow. This is the area. Am I correct, students?
Yes, sir.
The area which is normal to the flow. Okay, so now what happens here is it becomes minus del T divided by L by K. Am I correct, students?
Yes, sir.
So actually it is. We know that we know that minus T2 minus T1, assuming uh, heat is transferred from inner to outer. Okay, am I correct?
Yes, sir.
L by
Yes.
K. Okay. Now, what happens here is we know that the minus sign goes inside, so it happens. It becomes T1 minus T2 divided by L by. Am I correct, students?
Yes, sir.
So, which
Yes,
is
sir.
nothing but Q conducted, which is equal to del T divided by the resistance, conductive resistance. This conductive resistance is nothing but it is equivalent to this L by Ka. Is it fine?
Yes, sir.
Is it fine? Okay. Now, this conductive resistance mainly depends upon, oh, of course, it depends upon the thickness and it depends upon the area, L by A, which is also very, very important. But the main important property is the thermal conductivity. Am I correct?
Yes, sir.
Okay.
Yes,
If
sir.
the conductivity is lesser, naturally what happens is the resistance. Okay. The resistance, it will be offering higher resistance. Okay. Whereas if the conductivity is higher, then what happens is the resistance, it depends upon the conductivity value. Okay, now uh, so we also know that Q convection, which is equal to HA del T. Am I correct? Convective heat
Yes, sir.
transfer coefficient. When you have a solid plate, okay, which is exposed to air, okay, let air temperature be T infinity and solid temperature be T S surface temperature. Okay, then what happens here is HA into Ts minus T infinity. Okay, solid surface temperature minus ambient air temperature. Is it fine? T
Yes, sir.
infinity is air temperature, and so which this can be rewritten as del T divided by 1 by HA. Am I correct?
Yes, sir.
Where del T is Ts minus T infinity and 1 by HA is nothing but the convective resistance. Okay, students, or convective. Okay, is it fine?
Fine, sir.
Okay,
Yes,
ma.
sir.
Now,
Yes.
in this case, what happens is, okay, now if the solid size is so small and if it is quenched in a large quantity of or large volume of liquid, okay, which is at a very lesser temperature, then the conductive resistance, what is the conductive resistance? The conductive resistance is nothing but the L by Ka is very much lesser or very much minimum or it is negligible when compared to the convective resistance. Okay, because the solid size on shape is very less, whereas you have liquid which is at a very, the volume of the liquid is very that is a high or it's more, volume is more, so that what happens is you will be having lesser internal conductive resistance when compared to convective resistance. Am I correct?
Yes,
Or
sir.
the hot body is cooled, the hot body is cooled in a faster manner. Okay, so the process in which you have the internal conductive resistance or internal resistance is assumed to be negligible or it is very much lesser when compared to the convective surface resistance is said to be, if it is a heating process, then it is said to be Newtonian heating. If it is a cooling process, then it is said to be Newtonian cooling. Okay. If the fluid is at a lesser temperature and the solid is at a higher temperature, the solid cools. Right? Am I correct? Am I
Yes,
correct
sir.
or not?
Yes, sir.
All of you are able to understand?
Yes.
Dropping a
Yes, sir.
solid, high temperature solid into a large quantity or large volume of liquid which is at a very lesser temperature. So in that case what happens is the internal conductive resistance is very lesser when compared to the uh, convective resistance offered by the liquid. Okay, so convective resistance offered by the solid to the surrounding liquid. Okay, so in that case that cooling process is said to be Newtonian cooling and the heating process is said to be Newtonian heating. Am I correct or not? Am I correct?
Correct, sir.
Yes.
Yes, sir.
Okay. So in that case, what happens is you have this expression HA del T, which is equal to MCP. See, this is a little bit, and that is there is one more step which is missing. Let me write it out. It's a very simple expression, and I will write the expression also. Heat transfer to the body during dt, okay, which is equal to increase in the energy of the body during dt, or in other words the heat transferred or the heat lost by the body which is equal to decrease in the energy of the body. Okay, so in case of cooling, in case of heating, heat transfer into the body means the increase in energy. In case of cooling, the heat lost by the body will be equal to the decrease in energy. Okay, am I correct or not? Am I correct?
Yes, sir.
Okay.
Yes.
Now, what happens here is, let me write the expression here. Am I audible? Am I audible, ma?
Yes, sir.
Okay.
Yes, sir. Yeah.
Now, we know that by means of energy balance, Q conducted, which is equal to Q convected. Okay. That is the heat conducted, which is equal to heat conducted convected. So we know that uh, or in other words, that is the Q convected is also equivalent to the increase or decrease in the energy. Okay, or increase or decrease in the energy. If the energy is lost, we know that Q convected, which is equal to the change in energy of the body of the solid. Is it fine? That's what it was
Yes, sir.
mentioned. Increase or decrease in energy of the solid. Okay, so now we know that HA into Ts minus T infinity, which is equal to, or let it be T, not Ts. Okay, T me the temperature of the body and T infinity me the surrounding fluid temperature, which is equal to minus rho into V into C into dt divided by d tau, where capital T is nothing but temperature, denotes temperature, and small tau or tau denotes time. In some textbooks, they used to mention it as dt by small dt. So small t denotes time. Okay, in some textbook they used to denote it as t. Okay, so whatever which one is suitable for you, you can ask. Okay, you can write. Now I have written this rho v. Actually, this rho cv or rho vc, rho vc dt by dot tau or dou t by dou tau is nothing but we know that mass. What is mass? Density is equal to mass by volume, m by v. Am I correct?
Yes, sir.
Okay.
Yes,
So
sir.
instead of writing mc dt by dt, I have written rho vc dt divided by d tau. Okay, tau or t, whatever it is, whichever it is convenient for you, you can write. Is it fine, students? Is it fine?
Yes, sir.
Okay.
Ye-
Now let us
Yes, sir.
yeah. Now let us rewrite this expression. Is it visible to you? Is it
Yes,
visible
sir.
to
Yes.
you?
Yes,
Okay.
sir.
Let us rewrite this expression. Okay. When we rewrite it, we will be having what is the expression I have written earlier? Yeah. HA into T minus T infinity, which is equal to or minus rho VC divided by into dou T divided by dou tau. HA into T minus, kindly bear with me because I am writing on a smooth surface, which is equal to minus rho Vc into dou t divided by dou tau or dt divided by d tau. Okay. Now, what happens here is, let us take this rho Vc to the other side. Okay. And what happens here is Ha by rho Vc. Okay. Or take this minus sign also into dou tau, which is equal to dt or dou t divided by t minus t infinity. Is it fine?
Yes, sir.
Okay. Now, when you integrate this, what happens is minus Ha by rho. Yeah, let me rub it off. Okay. Tau, whereas time is 0 to t, okay, which is equal to, or 0 to tau, which is equal to integral. When it comes to this temperature, we have again initial temperature to final temperature. Am I correct?
Yes,
Am
sir.
I correct or not? We have
Yes, sir. Yes.
initial temperature to final temperature, dt divided by t minus t infinity. Okay, so when you integrate it, what you will be getting? When you integrate it, you will be getting when you integrate that expression, you will be getting natural log of, we know this, we know this, this is temperature T to T infinity. Okay, so natural log of dt by T infinity and dt divided by T minus T infinity, it will become natural log of this one. Am I correct or not?
Yes, sir.
Yes, sir.
Natural log of T minus T infinity, which is equal to minus HA. What is the other one? Minus HA by rho Vc minus HA by rho Vc into tau plus C1. Okay, now we are in a position to find out C1. When we apply at time tau equal to 0, t equal to t initial temperature. Am I correct? See, you are
Yes, sir.
having a solid, you are dropping a solid which is at a initial temperature Ti. After some time, it becomes temperature T. Okay, so when you substitute that to find out C1, this is the solution. Okay, so when you substitute at tau T equal to 0, okay, T equal to T initial. So natural log of Ti minus T infinity, which is equal to minus Ha by rho Vc into 0. So this expression becomes 0 plus C1, or in other words, C1, which is equal to natural log of Ti minus T infinity. Am I correct?
Yes, sir.
This expression C1. Now, when you substitute this in the original equation, you will be having natural log of T minus T infinity, which is equal to minus HA tau by rho Vc minus HA tau divided by rho Vc plus, in the place of C1, natural log of Ti minus T infinity. Am I correct?
Yes, sir.
Okay, so when this plus natural log of Ti minus T infinity goes to the other side, it becomes natural log of T minus T infinity minus natural log of Ti minus T infinity, which is equal to minus Ha tau divided by rho Vc. Am I correct?
Yes, sir.
Okay, now in natural log, we have this. We can rewrite it as natural log of t minus t infinity divided by Ti minus T infinity, where Ti is nothing but the initial temperature, T is the temperature after time seconds, and T infinity is nothing but the surrounding fluid temperature. Is it fine, students?
Yes, sir.
Now, so we can rewrite this expression as T minus T infinity divided by Ti minus T infinity equal to e power minus Ha tau by rho Vc. Shall I write them like that?
Yes, sir.
Yes, sir.
Okay, so that is what it was mentioned here. That is what it was mentioned here. So natural log of temperature at any instant time of time t, or temperature after time t minus T infinity divided by Ti minus T infinity, where Ti is nothing but the initial temperature and T infinity is nothing but the surrounding fluid temperature, which is equal to e power minus Bt, where B equal to Ha divided by rho Vc. So I have written it as Ha tau by rho Vc. What they have mentioned here is, they have mentioned this as B, which is equal to Ha divided by rho Vc into T. Is it fine?
Yes, sir.
Okay, where B equal to Ha by rho Vc, and T they have T is the time seconds. Is it fine, students? All of you are able to
Yes, sir.
note down how you got this expression,
Yes, sir.
students? Okay.
Yes, sir.
Now this B, what is this effect of B? So the B has a unit of 1 by S. Okay. So it is will be having a unit 1 by seconds or second inverse. Okay. And the reciprocal of B is usually the time constant. And usually you can see here, so when there is when the surrounding temperature is T infinity higher temperature and the initial temperature is low of the solid is lower. Okay, as I mentioned in the case of dropping a solid in a furnace. Okay, slowly the temperature increases. Am I correct? The temperature of the solid increases,
Yes, sir.
and after some time it will reach T infinity, which is nothing but the surrounding temperature. And you can see the curve. This if there is increase in temperature from Ti to T infinity, then it is said to be Newtonian heating or exponential heating process. Okay, it is said to be exponential heating process. Suppose if T infinity is lesser and Ta is higher, okay, then the curve will be coming backwards. Okay, then the curve will come backwards. Okay, or in other words, yeah, let me show it. I'm having that also. I didn't have a exponential cooling actually. So the exponential cooling curve will be more or less like this. So you will be having two types of curves. Okay, one is the exponential heating, the other one is the exponential cooling. So this is heating curve, this is heating curve, and this is cooling curve. Okay, students, the heating process and cooling process will be done in an exponential manner. Okay, and you should know one important dimensionless number, which is said to be Biot number. It is nothing but the ratio of conductive resistance to convective resistance. This is what I told you in the very first slide. Okay, the ratio of conductive resistance to convective resistance. What is conductive resistance? L by Ka. Am I correct?
Yes, sir.
Students,
Yes.
L by Ka. And conductive resistance is 1 by Ha. Okay, A and A gets cancelled and this H goes up, HL divided by K. Okay, where H is nothing but the convective heat transfer coefficient of the fluid with the solid, and K is nothing but the thermal conductivity, and L is nothing but the characteristic length. L is nothing but characteristic length, and this characteristic length is nothing but volume by area. Volume by area. Is it fine, students? Is it fine?
Yes, sir.
So HL by K, how you got that HL by K Bayard number, dimensionless number? So when you apply the units also, you will be getting the units. Okay, L will be in meter and H will be in watt per meter squared Kelvin, and H will be in K will be in watt per meter Kelvin. So watt per meter squared Kelvin, H into meter divided by watt per meter Kelvin. Okay, so Kelvin gets cancelled, watt gets cancelled, and here you have one meter. So meter and then this one. So you will be having a dimensionless number. The dimensionless number is said to be the Biot number. Okay, is it fine, students?
Yes, sir.
All of you are listening.
Yes, sir.
So what is Biot number? Biot number is a dimensionless number, okay, which decides whether the cooling is whether we have to assume it as a lumped parameter system or semi-infinite solid or infinite solid. Or in other words, if the Biot number ranges, it's very important. The Biot number ranges if it is less than 0.1. So immediately in case of whenever problem is given, a hot body it is dropped into a liquid at a very less temperature, or if a solid rod is dropped into a furnace which is at a higher temperature, means then immediately first you have to check Biot number. If the Biot number is less than 0.1, then you have to assume lumped parameter system. So the lumped parameter system is nothing but the system in which you will be dropping a solid into a high temperature zone or less temperature zone. Is it okay, students? Is it okay?
Yes, sir.
Or the lumped parameter system is the one in which the convective resistance is higher, okay, and the conductive resistance is lower. See, this is very high and this is very small, okay, or it is negligible. Okay, students?
Yes, sir.
Okay, so very practical example is the temperature sensor which we use in our heat transfer lab. Okay, the thermocouples, temperature sensors. Okay, when the sensors were brought into the high temperature zone, immediately the temperature changes. Am I correct? Thermocouples,
Yes, sir.
temperature sensors. Okay, so what happens is the thermal conductive resistance is very lesser when compared to the convective resistance. Or in other words, since the fluid is at a very high temperature, immediately when you insert the temperature sensor, okay, or the thermocouple changes its temperature and it shows the high temperature. For example, 100 degrees, 80 degrees, like that. Am I correct or not? Am I correct?
Yes.
So the conductive resistance of the material is lesser, whereas the convective resistance is higher. Okay, or the conductive resistance is negligible when compared to the convective resistance. In that case, the bad number will be less than 0.1, and that particular unsteady state heat transfer system is assumed to be lumped parameter system. Okay, LPM. And the second case will be bad number will be from 0.1 to 1, then it is infinite solid. We used to assume it as infinite solid. And if Bayer number tends to infinity, okay, greater than 1, then it is said to be semi-infinite solid. Okay, or in other words, Bayer number very much lesser than 1, Bayer number is almost equal to 1, Bayer number very much greater than 1. Okay, so the first case, lumped parameter system we will be using. Second case, we used to assume it as infinite solid. And the third case, we used to assume it as semi-infinite solid. Is it fine, students? Is it
Yes,
fine?
sir.
Fine, sir.
Okay, and for semi-infinite solid and infinite solid, we will be using the Hazel's charts. Okay, we will be using the Hazel's charts. Okay, and so first we will be having lumped parameter system, and we will be solving some problems in lumped parameter system. As I mentioned earlier, okay, so uh, uh, As I mentioned earlier, LC is nothing but L is nothing but the characteristic length. It is nothing but volume of solid divided by surface area of the solid. Okay, and uh, for plain wall, it is equal to uh, thickness divided by 2, and for long cylinder, it is radius divided by 2, and for sphere, it is radius divided by 3, and for cube, it is side divided by 6. Okay, so and you should also know that HA is into T divided by rho VC. It can be rewritten as uh, the product of Bayard number and Fourier number. And Fourier number is nothing but it is denoted by alpha T divided by LC squared. Okay, this HA T divided by rho VC, it can be rewritten as, okay, see what is this HAT by rho VC? We have already got this expression here. Am I correct?
Yes, sir.
We have already got this expression here. Okay, where is it? Yeah, HA divided by rho VC. Am I correct? HAT divided
Yes,
by
sir.
rho VC. Okay, so this HAT divided by rho VC, okay, we can rewrite it as HAT divided by rho VC, we can rewrite it as HT divided by rho C into, uh, because we know that volume by area is characteristic length. Am I correct? Volume by
Yes, sir.
area is characteristic length. So area by volume, I can rewrite it as 1 by L. Am I correct?
Yes, sir.
Okay, and
Yes, sir.
multiplying the numerator and denominator by L, we will be having HLC divided by K into K by rho C into T divided by LC squared. Am I correct? If you
Yes, sir.
multiply this by numerator by L and denominator by L or L suffix C, okay, you will be getting HLC by K into K divided by rho C, and again you have to multiply and divide it by K. You are inserting LCK in the numerator, and you are inserting LCK in the denominator. Am I correct?
Yes, sir.
See, why you are blinking here? Is it all of you are able to understand this? See, this is a very easy expression. Let me write it out. Have HA tau divided by rho V. Is it fine, students? Is it fine?
Yes, sir.
Okay. Now we know that volume by area is equal to characteristic length L suffix C or L. Is it fine?
Yes,
Is
sir.
it okay?
Yes, sir.
So I can rewrite it as H tau divided by rho into C into L. Is it fine?
Yes, sir.
Now let me multiply this by K into L in the numerator as well as denominator. Okay. So it will be equal only. Am I correct?
Yes, sir.
Okay. Now when I do it, what happens to the expression is this expression becomes HL by K into K by rho C into T by LC squared. Is it fine?
Yes, sir.
See, H HL H H is here, H is here, L is here, HL by K. So what is HL by K? The HL by K is nothing but the Bayard number. And there is one more thing which is known as alpha T divided by LC squared. Alpha is nothing but K divided by rho C, right? K divided by rho C, thermal conductivity divided by density into specific heat capacity, which we have already discussed. That is nothing but thermal diffusivity. The thermal diffusivity gives us an idea about how fast the heat diffuses into a solid. Is it fine? This K by rho C is nothing but
Yes, sir.
it is replaced by alpha. This K by rho C is replaced by alpha. So HL by K into alpha T by LC squared, where alpha T by LC squared is given as the Fourier number. Okay. So this HAT divided by rho VC is a product of Bayard number into Fourier number. Okay, so Fourier number is nothing but alpha t by L squared. All of you are able to understand this now, students?
Yes, sir.
Yes, sir.
All of you are able to understand this, how this HAT
Yes,
by
sir.
rho BC becomes a product of Bayard number into Fourier number. Both numbers were dimensionless numbers. Okay, so we have the product of Bayard number into Fourier number. Okay, so the Bayard number is the ratio of uh, conductive resistance to convective resistance, and Fourier number is given by alpha tau by L C squared, which is nothing but dimensionless number. Okay, which gives us a dimensionless time. Okay, so that's what it was mentioned here. Okay, alpha is nothing but thermal diffusivity, and characteristic length is nothing but L. Okay, and this characteristic length, it changes for different surfaces. Okay, for solid it will be thickness divided by 2, and for volume by area, characteristic length is nothing but volume divided by area. So, and for cylinders it will be radius divided by 2, and for spheres it is radius divided by 3, and for other for example, flat plate, when we take about flat plate, length, breadth, and height will be there. Okay, and when we talk about the surface area, we have to include the both the surface area, or let me draw it, or otherwise you people again you will be blinking. So this characteristic length, we have to find out the length, volume by area. Is it correct, students? I have told you
Correct,
that.
sir.
Now, when I have a plate like this, when I have a plate like this, so the heat is transferred in this surface, in this side as well as the other side. Okay. Am I correct or not? Hello?
Correct, sir.
Yes.
See, I am
Yes, sir.
talking about lumped parameter system. Don't think that one dimensional heat transfer. In case of lumped parameter system, the whole body is dropped inside. So heat is transferred from this side as well as the other side. You may ask, sir, even in this surface also the heat is transferred, but the heat transferred in this area is negligible when compared to the two sides. Okay. So let L, let this be H, and this be the thickness. Okay, when we talk about uh, volume, LH into T. Am I correct?
Correct, sir.
Am I correct or not? Length, height, and then thickness. Okay, and area, when we talk about area, this area 2 into L into H. So LH cancelled. So the thickness divided by 2. Is it fine?
Fine, sir.
Okay, similarly in
Yes, sir.
case of cylinder, when we talk about cylinder, we have, what is the volume of cylinder? Volume of cylinder, surface area of cylinder. What year? Students, all of you are there. What is the volume of cylinder?
Pi squared.
Pi r
Squared.
square.
Is it correct?
Correct, sir.
So what happens here? L equal to R by 2. Am I correct?
Correct, sir.
Correct or not, ma?
Yes, sir.
What happens in case of sphere? 4 by 3 pi r cube divided by 4 pi r squared. Am I correct or not?
Yes, sir.
Yes, sir.
What
Correct.
Yes,
here?
sir.
Students, r square gets cancelled. So you will be having only 1. 4 pi gets cancelled. So what it will be? R by 3. Am I correct?
Yes, sir.
Yes, sir.
Yes, sir.
And for cube, when you take cube, what is a cube, ma? It will be having same dimensions in all the 6 surfaces. Am I correct?
Yes, sir.
Yes,
L
sir.
cube divided by 6L squared. If you have assumed that, so L by 6 or A by 6. Okay, side or L equal to side of the cube. Or put it as A. A by 6 equal to L. Is it fine?
Fine, sir.
A equal to side of cube. So this is very important, ma. The characteristic length. Okay. So in case of plate, it is thickness divided by 2. All of you are able to understand how I got this T by 2, R by 2, R by 3 and A by 6.
Yes, sir.
Yes, sir.
I won't
Yes, sir.
be explaining it to you again and again. Okay. And what I will do is, yeah. Now, let me give one problem so that all of you please solve this problem. All of you please try to solve this problem. Okay, I will give you the if you are not able to solve it, and yeah, in the chat box I have given it, ma. Is it visible
Yes,
to
sir.
you?
Sir.
Yes, sir.
In the chat box I have given. If you are not able to solve it, then I will solve the problem on Thursday's class. Is it fine?
Fine, sir.
Sir.